Let's go ahead and derive the fourth of these equations here. I'm not going to derive the fifth one. It's really algebra where you put some equations together. If you want to see it, let me know. But let's go ahead and derive this fourth one as our last one for equations of constant acceleration with these as our given. So let's figure out the idea of how the fourth one came about. There's lots of ways to derive this, but my favorite way to derive this equation right here is definitely with a velocity graph. I'm a big fan of those. So I'm going to draw a velocity graph that kind of represents an accelerating object. So maybe it starts at one velocity and ends at another velocity. And so it constantly changes velocity, and let's say it takes t seconds to do so. And just because I know I'm going to need it, I'm going to try and repeat the same graph over here with the same basic idea of starts at one velocity, ends at another velocity, and takes t seconds to change velocity. Again, we're looking for an equation for displacement. Displacement is the area under a VT graph. So I'm looking for the displacement of this object. I'm really looking for this area right here. It's a trapezoid area. So we're looking for the area of a trapezoid. Some of you might even recognize this as a trapezoid formula. And so you could just say, oh, it's the trapezoid formula. You'd be set. You kind of would understand where that comes from right away. But in case you don't know the trapezoid formula, I'm much more comfortable with finding areas for rectangles, and I want to show you that this area on the left is the exact same thing as a specific area on the right. If I take this midpoint, the midpoint's like the average, vi plus vf over 2, the exact center between those two, and I draw a flat line across and just pretend that my object went at the average speed the whole time, then I can say that that flat line that I just drew, the area under that, the area of that black rectangle, is the same as the trapezoid area. Kind of from a logic standpoint, it's like saying if I went the average velocity the whole time, I'd still end up going the same displacement as if I took this motion. But another way to argue that those areas might be the same is to say, well, it's kind of weird because it looks like there's this extra triangle that I'm accounting for in this, but then you can think, oh, but it's missing this top triangle over here. And so you can probably convince yourself that this triangle and this triangle have the same area. So I'm getting a little extra here, but the same missing there, and it works out to be the same. So we want to say the area of this black rectangle then, and area of a rectangle is length times width. And if I go this side by this side is now vi plus vf over 2. This side is now t, and we're done. We've derived our fourth equation, and the last one we'll do, if you want, we won't do. If you want to see it, you can kind of put them together from an algebraic standpoint. The first four over here, the first four are the ones that really get the physics concepts the best. And this is just, hey, when you come to a problem where you don't know time, you don't need to know time, this would be a good one to choose.